Hello, I'm Tom Benton. I'm a statistician at Cambridge Assessment, and I'm going to talk about some work we've done working out how we can use all of the data that we hold to help us decide where to put grade boundaries. Now, although we can use lots of sources of evidence for this talk, I'm only going to talk about the statistical methods in this video. This work was actually first presented at the AEA Europe conference in November 2017. So, statistical evidence has been used in awarding for a long time. The basic idea is if we have thousands of students who take a particular exam and they're from the same schools as last year, and we had thousands last year, and there's no obvious change in entry policies or anything like that, then it's reasonable to expect that the percentage of students getting each grade this year will be close to where it was last year. We expect some stability. And using that assumption, we can decide where to put grade boundaries. But what in more complicated situations? What if we only have a few hundred students taking the exam? Or we've got lots of schools dropping out, switching subjects, so new schools coming in? Or if there's a change in entry policies, for example, schools encouraging lower ability students to take more exams, have a go at more of them. In those situations, we can't necessarily expect to see stability. As such, this simple form of statistical evidence isn't as useful as it could be. So, what do we do? Well, we're going to capitalise on the fact that we're a large assessment organisation. Picture here maps out our data. Each circle represents an assessment. The more people take an assessment, the bigger the circle. We've got lines between the circles indicate that at least 200 people take one assessment alongside another. So we've got a statistical link. For example, some people taking a biology assessment will also be taking history. Some people taking maths will also be taking geography, and so on. And this linked data from one subject can tell us something about the students taking another subject. In fact, on average, each assessment is linked to 16 others. So this means when we're trying to set grade boundaries for biology, for example, we could pull in data from other subjects, history, English, maths, bring it all together to tell us something about our cohort of students and tell us maybe something about where the grade boundary should be. More precisely, our data is going to be to join all our data together. And once we've got it all joined together, somewhere in the world, we'd hope to find stability somewhere. And then we can use that to help us set grade boundaries across everything. First, we need to link our data together. To do this, we use statistics to create a single measure of ability that we calculate for students and is comparable regardless of which assessments they've entered. This measure is called the ISORG, which stands for Instant Summary of Achievement Without Grades. Crucially, and I'll show you how in a minute, we're able to calculate this measure, the ISORG, before we've set any grade boundaries. It's just going to be based on raw marks, and then we're going to be able to use it to set those grade boundaries. So the equation to calculate the ISORG is in this slide. The idea is that we assign one number to each student, the ISORG essentially estimating how clever they are. Then we have two parameters for each assessment, showing the link between this overall measure of ability and scores on each individual test. All these pupil abilities and assessment parameters are estimated so that our predictions of how well students will do in individual tests are as accurate as possible across everything they've done. Remember, we've only got one measure of ability, the ISORG for each student, but they'd have done lots of different assessments. The rest of this presentation will explore whether creating this ability measure and then using it to maintain standards actually works. So before trying it out on maintaining standards across time, we're first going to test out whether it can be used to maintain standards from one assessment to another taken within the same year, within the same examination session. Here's an example of how we do it. First, we find two assessments that are usually taken as a pair. So in this example, the pair are an assessment called Science 3 and another called Science 5. I've used simplified names here rather than the long assessment codes that we use in practice. Now, Because these two assessments are taken by the same people, it's easy to map each mark on one test to a mark on the other test that's equally difficult. So, for example, this is the way we do it. I know from charts not shown here that 16% of pupils score 20 or below on Science 3. I know also that 16% of students score 18 or below on Science 5. Therefore, a score of 20 on Science 3 maps to a score of 18 on Science 5. They're at the same percentile. And I use that same method, called the equipercentile method, across the score range to get that mapping. Now that was easy because both tests were taken by the same people. But what I want to see is whether I could reproduce that mapping between Science 3 and Science 5 if they were done by different groups of people. So I'm going to split my students into two groups. And to give myself a tough challenge, I'm not just going to do it at random. I'm going to deliberately set it up so that high ability students are more likely to be in group 2, that's going to be the group who are taking Science 5. Next, I imagine that people in group 1 haven't done one of the tests, so I delete their scores on Science 5. For group 2, I delete their scores on the other tests on Science 3. I've now got two different groups who've done two different tests. How am I going to tell how much harder Science 5 is than Science 3? I can't just compare distributions of scores because it's different sets of pupils and one group's cleverer than the other. Well, I'm going to use all our data from other assessments. Some people have got data from a religious studies exam, other from maths exams, lots of other data I'm not showing here. We're going to bring it all together to help us compare the difficulty of Science 3 and Science 5. How am I going to do it? This is where the ISORG comes in. First, I calculate the ISORG for all students, not just those doing Science 3 and Science 5, everyone, based on all the exam scores that I haven't deleted. The chart here shows distributions of the ISORG for my two groups. As you can see, the group doing Science 5, group 2, are of higher ability. Reflects the way I've set it up. Next, to make things easier, I'm going to break the ISORG into 10 categories. That's going to make the next step a little easier. If I had the full population, everyone I've calculated it for would actually have even numbers in each category. For the people doing these particular tests, there were more students in the lower categories. Now, I weight the data so that group 1 and group 2 are equivalent. This is like taking samples from our data so that within each achievement band would have the same number of people in group 1 as in group 2. It would match up. This would mean that our two groups are roughly equivalent. Now that our two groups are in some sense equivalent again, I can go back to just looking at score distributions using the equipercentile method. What percentage got 20 or below on Science 3? What's the equivalent mark on Science 5? The same procedure I talked about before. And this can re-estimate how score on one test maps to each score on the other. Once I've done this, I've got that line there, I can compare it to the correct line based on the fact that in reality I've got lots of people who did both that I estimated earlier. And when I do that, I see that my method using the ISORG is on average accurate within just over 2.5 marks. To see if this is any good, I compare it to other approaches I might take to the same problem. A popular source of data for tackling this issue in England is to use Key Stage 2 data. So these are data from primary school tests which are taken by the majority of people. They've all done the same test, so it can give us links between different assessments. If I use that information to make the link between Science 3 and Science 5, I end up with less accurate results, 3.5 marks off. Alternatively, I could explore what happens if I just ignore the differences between the two groups. Just assume that group 2, assume they're no cleverer than group 1 and imagine that difference wasn't there. If I do that, ignore the differences, I end up being 4.5 marks inaccurate on average. So I've only shown the results for one pair of assessments here. Results for more pairs and looking at other methods of doing this same problem can be found in the conference paper on our website. However, one thing we consistently find in all those results is that using the ISORG leads to more accurate results than using Key Stage 2. So what about if we want to test the efficacy of the ISORG for maintaining standards between years? Well, we use a similar approach. This time we're going to split the entire cohort of GCSE candidates, 500,000 pupils, nearly 5,000 schools, into two groups and treat the two groups as if they were two different years. And again, I'm not going to do this completely at random. I'm going to set it up so that high-performing schools, based on their average GCSEs, enter more people in this imaginary year 2, and where low-performing schools enter more of their people in the imaginary year 1. They've decreased their entry. Now we've split our data into 2 years, we're going to use a similar approach to equating as before. Estimate the ISORG, link between assessments using the ISORG. However, the ISORGs in each year are estimated independently. There's no pupils in both groups. Pupils are either doing their exams in year 1 or in year 2. This means the ISORGs themselves aren't yet directly comparable. To overcome this, we use the principle we talked about right at the beginning. We've pulled all our data together, so we're going to find stability between years somewhere. Specifically, we're going to look for schools who have entered the same number of pupils, roughly, in Group 1 or in Year 1 as they have in Year 2. Stable schools. And we're going to use these stable schools to calibrate the ISORG in Year 1 to the ISORG in Year 2. And then we've made them comparable and we can work as before. So to complete our experiment, we're going to equate each exam in Year 1 to the same exam in Year 2 via the ISORG. So it's the same process as before, but in this time we've got two different groups of students who have actually done the same exam. Will the data be able to correctly identify that the tests done by different groups are actually equally difficult across the score range? Because they're the same tests. So getting 20 marks in Year 1 ought to map to 20 marks in Year 2. If the method's working, they'll notice that all the tests are the same difficulty between years. I'm going to compare the accuracy of the method using the ISORG to two other methods. One again using Key Stage 2 to make that link between Year 1 and Year 2. Or I could just look at one assessment at a time and say, just within this little bit of data, within this assessment, can we find some stable schools, say, within history? And then just using that data, don't worry about the pooling it all together, just within them, let's find some stable schools and use that to map difficulty from one group to the other. So I did this experiment for over 200 assessments. All the accuracies are shown in this chart. The chart shows how accurately each method reproduces that correct mapping between scores, between what is in fact the same test, in different years. The blue dots are the accuracy of the ISORG. Using stable schools within assessments, that's red. Using Key Stage 2, those are the green dots. I've also added lines which show how the trends in accuracy change as we increase the number of students taking an assessment. So it shows the difference between large entry assessments and small entry ones. What do we see? Well, Key Stage 2 generally has the worst accuracy. I've deliberately set up the experiments. We've got big differences between groups, and the data from primary school assessments just isn't strong enough to account for that. Looking at assessments individually and finding stable schools, the red dots, that works okay if we've got assessments with large entries, so we can find lots of these stable schools, find lots of big stable schools to work with, but it's not so good otherwise. In contrast, using the ISORG does seem to work across the whole score range, giving pretty accurate results. Low error. So to summarise, we can use all our data to get a single measure of ability, the ISORG. We can use stable schools to calibrate it across years, and once we've done that, we can then use it as one source of evidence to help us maintain standards over time, using all our data to help us maintain standards. A conference paper giving a lot more detail about this research is available on our website. To take a look at that or to view any of our other research, go to cambridgeassessment.org.uk/our research.